So, cyclohexane is one of the more common rings. It's probably the most common ring with all single bonds. Substituted cyclohexanes occur widely in nature, so they show up in lots of places. We know that it's free of angle strain and torsional strain, and that's because it creates this sort of this bent shape. We usually call it a chair conformation because it looks like a chair. Let me pull up my pointer. So it's got this kind of a point up here, the head, and then the feet, and it's got this chair shape. And so it bends into, and what happens is that it has alternating carbons, and all 6 carbons are tetrahedral 109.5 bond angles. So if you look here, what they're telling you is they're looking down this bond at number 1, 2, and number 5, 6, these parallel bonds. And that's what we see over here with the Fisher projection. So here's carbon 1, here's carbon 1 in front, here's carbon 2, that's the big circle back here. Carbon 3 is this one down here, and then it's linked over to 4, which is the back one here, 5, which is the closer one, and then 6, which is right here. And what you can see when you look down those two bonds, 1, 2, and 4, 5, is that everything is perfectly staggered. And so the two CH2 groups are in the staggered position. All the H's, none of the H's are eclipsed at all. And so it's actually 0 torsional strain. It also has 0 angle strain because again, all these bond angles are 109.5. This is sort of what the molecule looks like with the kind of molecular model shape. So this is called the chair conformation. All right, this you want to probably study quite a bit. How do you draw a cyclohexane on a piece of paper? So I recommend following this. So draw your parallel lines. Then on the right-hand side, it's going to go up. So notice that they're slanting downward. So from the ones that are at the bottom of the slants, that is going to go up. So that's your angle that goes up. And then from the top of the parallel lines, it's going to point down. So you see that. So we've got parallel lines, then one up, and then one down. The bottom goes down. So you want to probably practice doing these a little bit because you're going to be drawing some. Now, there's 2 different types of hydrogen in a cyclohexane. So there's 2 different positions. So with all these red ones are sticking straight up or straight down from the carbon. Those are called axial, because they're with the axis of the molecule, up and down, up and down. And then all these blue ones are called equatorial because they're around the equator. And they're all coming out kind of at an angle, slightly up, slightly down, slightly up, slightly up, slightly up, slightly down. That one's slightly down. So they're alternating. There's 6 equatorial. So on each carbon, you have 1 axial and 1 equatorial. 1 equatorial, 1 axial. 1 axial, 1 equatorial. 1 axial, 1 equatorial. When you draw your cyclohexane, if you want to draw in your hydrogens, notice that the axials go up. Whenever the point goes up, the axials go up. And wherever the point comes down, the axials come straight down. And then the equatorials are actually parallel. So this line is actually parallel to this line. And this one is parallel to, let's see, to this one here. So it's always parallel to the line that's not part of the angle. So because there's 3 of them. So again, this is just another view. This is sort of the atom filling, the molecule filling structure, and these are the balls and wedge, or the bonds with the balls. So on every carbon, again, on every carbon in the cyclohexane, there's one axial. So this one, this one, this one are the axial. And then on the bottom, if you flipped this over, you'd have 3 on the bottom. So they're going straight up and down. And then you've got the 6 around the equatorial. Same thing here. We got up, up, up. And then on this carbon here, there's one going down. This carbon, there's one going down. This carbon, one going down. And then there's one around the equatorial all the way around. So here's what I was talking about before. Once you draw your chair conformation, then again, wherever the points point up, so I would always draw in your axial bonds first. So whenever it points up, the axial goes up. And then whenever it points down, the axial goes down. And then the equatorial, as you can see, so here on this point, it's these 2 carbons coming together. So this equatorial is parallel to this one, and this one's parallel to this one. So you find the 2 that it's attached to, and it's parallel to the 3rd one, because these are parallel, these are parallel, and these are parallel. So we've got our 2 equatorial this way, and our 2 equatorial this way, and our 2 this way. So if you put them all together, you've got your axial and equatorial. So I would practice making those. All right, so here's a fun thing that happens to cyclohexane. Cyclohexane actually is moving, and what happens is it does what's called a ring flip. So what happens is all of the axials become equatorial. So this red one comes down, and it's here. This, and it's sort of hard to explain on this, but notice that this circle is colored. This, if you call this carbon number 1, once it comes, it'll flip downward. So the blue will be down and the pink will be equatorial, and the blue will be, and that's this one. So this peak comes down and becomes this carbon. This one flips up, so the blue's up and the pink's equatorial. This one flips down, where the blue's down and the pink's equatorial. This one moves up, so the blue is up and the pink is equatorial. And then the next 2, this one will flip. The pink will go equatorial and the blue will go down. So we've got the axial and equatorial. And then finally this one, the blue flips up and the pink becomes equatorial, and we have this carbon. So you might take a little bit of time and study each one of these and what happens. I wish I could show you, but you pull the top one down, push the bottom one up, and everything else will flip. I'll try to do a video of a ring flip, or I've got I think some links to videos that I will post on Canvas, and also I'll maybe try to do a little video myself. So if there's if it's all hydrogen, so if you just have cyclohexane, then it just can flip back and forth, and there's really no difference between the 2 of them, because you've got 6 hydrogens that are equatorial and 6 hydrogens that are axial, and it doesn't really matter which hydrogens are which. But a lot of interesting things happen when you have a monosubstituted cyclohexane. So if you've got something attached to it, and this is kind of a weird graph too, which I'll explain in just a second. So if you have a monosubstituted cyclohexane, the 2 ring flips are not equivalent. So it turns out that if something is in the axial position, it's higher energy than if it's in the equatorial position. So let me say that again. If something's in the axial position, it's at a higher energy than something in the equatorial position, and I'll show you why on another slide. If it happens to be methane, a methyl group that's attached, that difference is 7.6 kilojoules. Not that you need to remember the numbers or anything. What they're saying here is, all this is saying is that if you have two different, if there's a difference between the axial and equatorial, then if there's no difference, then you're going to have about half and half. The more difference there is between axial and equatorial for that one substituent, then the more you're going to have of the stable isomer in the equatorial position, and the less you're going to have of the isomer in the equatorial position. All right, so here's a picture. So this one has one of each, but remember that if it's mono-substituted, it'll just be one, and it'll either be in the axial position. So here's a methyl group in the axial position. Here's a methyl group in the equatorial position. So here's a mono-substituted cyclohexane. So here, the CH3 is axial, and here's the hydrogen. Now notice what happens. Remember, this one, when it flips down, becomes this carbon right here. So notice that this point comes down, this point goes up, and then these two switch from being sloped downward to being sloped upward. So that's what happens. And if it helps you to number the carbons to start with so that you follow it along. So when this one comes down, if this is carbon number 1, now this is carbon number 1. So it's really just coming down, and then just follow along. So this is number 2, 2, 3, 3, 4. 4 is what goes up here. 5 is right here. And then 6 is right there. So again, I would recommend practicing it a little bit. Here are these. I can't really show you these animations on this recording, but I will put a link again in Canvas so that you can watch some of these videos. But what's really important, this sentence right here, when a substituent goes through a ring flip, keep in mind that it always stays on the same side of the ring. So what do I mean by that? Notice that I've got my my pointer on this carbon number 1. The CH3 is axial and the H is equatorial, but no matter what, the CH3 is on top and the H is on the bottom of these two substituents. This is the top one, this is the bottom one. When it does its ring flip, now the CH3 is equatorial and the H is axial, but see, the CH3 is still the top and the H is still the bottom. So they're not changing places or anything. I mean, they do become, one becomes axial, one becomes equatorial, or axial equatorial, but that ring flip doesn't change which one's on top and which one's on the bottom. So that is a really important point. So make sure you understand that, maybe listen to it again if you can, because they're not changing places, they're just changing whether they're axial or equatorial. So I was saying that if something is in the axial position, it's at a higher energy, which is less stable. So the reason why is because it's something called 1,3 diaxial interactions. And what that means is when you've got these axial carbons, let me see if I can draw it here. To go up a little bit. Not very good with my mouse. If you've got these, you've got 3 axials on the same side. So here's an axial, here's an axial. And when something's axial, it's interacting with these other axials. I'm not very good at drawing that. Let's try another color, blue. So it's like interacting with this one and this one. This is called a 1,3 diaxial interaction because it's if this carbon is number 1, then it's interacting with number 3 in either direction. That would be number 3 from there. So these are diaxial interactions. What that means is that if these were hydrogens, they're too close to the methyl group. If it's in the equatorial position, then it's not in anybody's way. So here's just a better picture of it. So here's the methyl group, and here's if you count that as number 1, then this is number 3, or if you go in this direction, that's number 3. So these are 1,3 diaxial interactions. So the methyl group is it's a steric energy, or steric problems, because they're too close to each other. But notice that if we do a ring flip, now notice all the blue ones that were equatorial have become axial, and all the red ones that were axial have become equatorial, but also this methyl group has become equatorial. Now there is nothing, it's not interacting with any of these axial hydrogen, so it has no energy. So this is about 7.6 kilojoules energy higher than this. So substituents like to be in the equatorial position. And so that's really easy. If you have a mono-substituted, the more stable compound is going to have the substituted group in the equatorial position. It's going to, so unlike cyclohexane that flips back and forth no matter what, just kind of, if it's got enough energy, it'll be flipping back and forth. Most of the time, it depends on the temperature, but in this case, probably the majority of the compound will be stuck in this position, whereas a very much smaller percentage will be in this position, which is what that first graph was saying. The bigger the energy difference, the bigger the concentration of the more stable equatorial position for the substituent. Here on these pictures, you can really see it. They're just kind of in each other's way, whereas if that group's on the equatorial, then it's not in any way there. Here's another example. So the bromine is interacting with these hydrogens. Those are the 1,3 diaxial interactions. And then when you do a ring flip, the bromine is equatorial. So the equatorial is going to be a lower energy than the axial. This graph sort of, I'm not going to ask you any particular numbers unless they're given to you. It's not anything you have to memorize. But what they're showing you here is sort of whatever the substituent is, what kind of energy interaction is there between Y and H. So we were looking at the methyl group. The methyl group, it's 3.8. Remember that there's 2 hydrogen. There's another one here. Let's draw that in. There's another H right here. So we double whatever it is. So if Y happens to be methane or methyl group, then it's 3.8 times 2. That's where the 7.6 comes from. We were just looking at bromine, which is lower energy. You can see that axial, bromine's a smaller group than a CH3 group, so it has a lower energy. It's not as much in the way of the hydrogen. So this would only have a 2 kilojoule per mole energy between the bromine and the 2 hydrogen. So going back to that first graph, this one would be closer to 50-50, where some were axial and some were equatorial, because that's a much lower energy than, say, methyl. Methyl might be maybe 75-25, something like that. I'm just making up these numbers, but there will definitely be more of the CH3 in the equatorial position. What if you get a group like a T-butyl group, C with three methyl groups attached? So this is a huge group. So you can see it's much higher energy, 11.4. So that'd be 22.8. So that's going to be almost 100% in the equatorial position. And so you can kind of get the idea. So the bigger the group, the higher the energy. So why do you suppose a cyano group causes practically no 1,3 diaxial steric strain? So actually, if you look on the previous slide, I think it was each CN H interaction is only 0.4 kilojoules. So overall, it's only a difference of about 0.8 between the two hydrogens. So that's pretty low compared to 7.6. So it's not even, 0.8 versus 7.6. So a methyl group will really make a difference, but a cyano group doesn't. And you think, well, I wonder why, because CN, that sounds like a big group. But here's what it looks like. So here's a ethyl group, right? So that had it's a 4.0 and then another 4.0, so 8.0 kilojoules for this to be axial. So it's going to be 96% of the time this is going to ring flip and the ethyl group will be equatorial. Here's what a cyano group looks like. So it's, it's straight because of that triple bond. So you can see that it doesn't get in the way of the hydrogens nearly as much. And so this has got the much lower energy of interaction. These diaxial interactions will be much smaller. So maybe about 67% will be equatorial. So there still will be more equatorial, but only about 33% will still be in the axial position. So let's going back to that graph I was talking about. The greater the energy difference, the more percentage will be in the less will be in the axial and the more will be in the equatorial position.